but we are going to explore the graph G transpose. Okay, so this is what we need to do, because we need to first figure out the ordering, and once we have it we need to reverse all the edges, and then once we have those edges we now need to figure out all of the nodes that are connected to our particular graph. So if you remember this particular original example that we had, here we had here we had this set of ordering, right? A, B, E, F, C, D. We reversed all the edges that made A, B, E, F, C, D, right? All the reversed edges. And then we are going to start off with the same ordering. Remember that this is, before I begin explaining that, I have a question. Once I reversed these edges, is this still a valid topological order? Is this, so let's say that I've reversed these edges, the original graph just has reversed edges. No, Brian Akins, this is not a valid order anymore, right? Because A is not a source anymore. A is now a child. A should be in here instead, right? Not at the front. Exactly. So this is not a valid topological order, but we are still going to maintain the old topological order from the original graph, but we are going to explore on the transposed graph, right? So let's look at an example. So let's say that this is the reversed edge graph. Now we are still going to use the old order. So the first source node for that particular old graph was E. In this reversed graph, what is E? E is a sink node, isn't it?
Yep.
Yep. Okay, so now if we explore E here, because we are exploring E because E was the source node of the original graph, that is why we are exploring E first. But once we start exploring E in this reverse, from this reversed graph, the ordering is, so let me just clarify it a bit better. The ordering is given by the original graph, but the explore is being performed on the transposed graph. Okay, so we first explore E, and in this graph, we see that E is a standalone node. So that gives you one particular node done, nothing to explore here. So we have one strongly connected component. Now we delete E from this entire graph. E does not exist anymore. Then we move on to the next thing to cover. So in that scenario, this is node B, right? So for node B, we are basically going to, let's see, can I, give me one second. Image. Okay, so we are done with E. The next node in order is going to be B. Again, B is a sink node, and in that scenario, again, B is a standalone node. So we are done with B and we stop. Similarly for A, in this scenario, A has two edges coming inside. So we don't bother about that. A also has two edges going outside, one to B, one to E. However, both B and E are already taken care of. We are done. It has been visited. So essentially A is a standalone node, right? Explore for A would just result in A, because we have already covered E and B. And because we have ordered it using the topological sort, that is why once we take out E, once we take out B, all the strongly connected components remain, but all the edges that are normal edges go away, because we are starting from the source of that particular graph. So once we start with A, B and E are already done. So we are done with A. And so A is a standalone node as well. Okay. The next node in order is H. So we start with H. Now comes the fun part. H is connected to I, so I get I, so H and I. I is connected to G, that is fine, G, so I get H, I and G. But G is connected to B, but I don't care because B is already done. G is connected to H, and we are already doing that. So G, I and H, or H, I and G, form the first strongly connected component of your graph, right? So now we are done with H. We go to G, but G is already done. So we move on to I. I is already done. So HGI is done. The next thing that we look at is C. Now for C, we cover all of these nodes here, C, J, F, and D. That gives you the first strongly connected, second strongly connected component of this graph. And now basically we just remove J, F, and D because we are already done with that. And that gives you these 5 strongly connected components, E, A, B, HIG, and CJFD.
And just to clarify, E is considered an SCC even though it doesn't have a loop, right? Because it's
yes, yes, all single nodes that are not part of an SCC, or yeah, all single nodes that are not part of an SCC is again an SCC. Okay. Now for this, now basically this gives us the ability to figure out strongly connected components because of the property that all of the, so the property essentially is if I start from, let's go back to that diagram. So the point is, if I start from a sink node of a graph, where, I mean, if I start from a sink SCC of a graph, in that scenario, I am able to extract all the entirety of the strongly connected component, in this case CJFD or HIG. Let's go with CJFD. This is a sink node. If I can figure out that these are the nodes for a sink node, I am able to extract this particular set of nodes as an SCC. However, figuring out the nodes of an SCC is in the sink SCC is difficult because you have multiple nodes going out and in, and it's a strongly connected component as well. So, but figuring out a node in a source SCC is much easier. And that is why we reverse the set of edges, and that makes this CJFD from a source node, from a sink node into a source node. And then we can basically pick one at a time. So we start with E, we start with then A, then B, then C. And since this particular C in the reverse edge is also connected to A, but we have already done taking care of all the source nodes. And why? Because a source node will always have a higher post number than its children. So if we take care of the parent, there is no case where a child would go back to a parent, right? Because we are done with the parent, because we are starting from the largest post visit number. And since we are starting from the largest post visit number and we are done with all of those nodes, the next basically thing, if we lob off one particular set one at a time, we are essentially extracting one strongly component SCC at every iteration. Now, does that make sense?
We use topological sort to find all of our source nodes, and then we just flip everything. Yes. And then that way we know. And then if we're, since they're already topological, we keep that topological sort. And then now when we go iterate through it, then we'll be finding all the sinks, right?
Yes. Now when we iterate through the transpose of that graph or the reverse graph, then we would find the
original topological order.
Yes, because in the original graph, the thing that was the sink, we wanted to start from there, right? So if we go back to that particular example here, right, this was a sink, right? This BEFCD was a sink and we wanted to start from here. But finding a node in a sink is difficult, but finding a node as a source node is quite easy. So in that scenario, we wanted a way where this particular component became a source node. And that was the reason we reversed all the edges and made it into a source node. And since this was a source node and we are lobbing off things in that particular order as the original graph, as we see here in the original graph, A had a connection to this SCC. But once we reversed it, A became disjoint and then we can just cut it off if there is no connected components there. And then for any node BEFCD, if we just explore from these nodes, we will get or extract the entirety of the strongly connected components. So Every time we call explore again on a new set of unvisited nodes, that gives you a new strongly connected component. Here we call explore for E, that gives us 1 and it is done. Then we call explore for B. Again, it's done. That's the second component. Then we call it for A, same thing. Then we call it for H, and that gives us HING. So that is the fourth component. G and I, we do not call explore because those are already explored. For C now, we again call explore. So that is the fifth component. That gives us CJFD, and that gives us all of our 5 components because J, F, and D have been traversed. Any questions about this? Is it a bit more clearer? Now, if it's clear, if I ask you that given a graph, output all the strongly connected components of this graph, would you be able to find out all of those components? Anybody else of the 37 students in this class? I see one, I need 36 answers. If you still see that there is some confusion, just let me know. I need to understand what might be the hiccup. So in order to understand strongly connected components, there are 2 ways of understanding this. The first thing is, this is the algo. You get your post visit numbers, you get your reversed graph, you apply this in this order, and you get your strongly connected components. The algo is simple enough. However, you need to understand why this algo works. Right? The algo works because of these properties. Let me bring that up. So the properties are, if we apply the explore subroutine at a particular node U, it will terminate. If it is a sync node, it will terminate once it has covered all of the nodes in the sync strongly connected component. So once we have that particular set of nodes, the next thing that we need to do is move on to the next sync. But that becomes difficult, right? Because those are all parents. But if we reverse this graph, that allows us to just delete out the source nodes. And since we're deleting out the source nodes, we know that our post visit numbers are still in order, because all of the children nodes will always have a post visit number lower than our source node. And if we just now, instead of doing it in the forward order, we do it in the reverse order, we get 2 benefits. One is, it is easier to identify which nodes belong to a source. And the second is, even in a reversed graph, the strongly connected components still stay strongly connected, right? Okay. So basically, once we reverse it, the node with the highest post visit number now becomes the node with the lowest post visit number. And that is why once we reverse it, let's say that C and C prime are 2 components, and there is a node from C to C prime. We know that C prime would always have a lower post visit number than C, because there is this edge. So if we always cover C first, then in that scenario, there would be an edge connecting C prime, and that would cover the entirety of C and C prime, because C and C prime are 2 connect SCCs with an edge from C to C prime. So if we start from C, it would cover C and C prime. However, if we reverse those edges and again start from C, it would only cover C, because C is still a strongly connected component, but it would